Welcome, everybody, to Mark Voids a Warranty. And guess what we're doing? We're voiding a warranty. And because my friend Christian is watching, we're going to void a warranty with a hammer. That's right, a hammer. It's going to be fun. You're going to love it. Don't even sweat it. I'm just going to do it like that. It'll be fun. Anyhow, today we've got the Ubiquiti Unifi what is it, the thing called? Just an access point, I guess. I don't know which version this is, but the Ubiquiti Unifi AP access point. And this has provided wonderful service to the house over the last few years, except it is now end of life. It no longer serves really any useful purpose, actually. In fact, I just swapped it out with its little brother, the Unifi Access Point HD, the other day. So let's see what's inside. This is a pretty cool device. It is power over Ethernet using some weird protocol. I don't know what it is, but it's provided with this little adapter here, and that's what we're going to play Mark Smash on. Now, since we did just start the stream and nobody's watching, we'll start with the PoE adapter. This is a little molded, pretty sure it's glued together, device, and you plug one end into your network cord and the other one into your device, and it turns out with the 8 conductor pins that they use for networking, most devices only ever make use of 4 of those pins. That leaves 4 pins available for other things, and Ubiquiti found a way to inject electricity into it. There are a few PoE protocols, but I mean, I don't know why they have their own separate thing, but you can't just plug it into another PoE switch and have it work. It didn't. I don't know what the issue was. So, how do you get these things apart? They're glued at the seam with a hammer. Here we go. Easy peasy, lemon squeezy. And here is our first board of the day. How exciting is that? Let's get zoomed in a little here. So this is just a tiny little inverter board. We've got line power coming in here, alternating current. Looks like they went ahead and ran a ground wire all the way over. I don't know why yet, but maybe we'll figure that out as we go through here. We've got the hot lead coming over to this edge of the board, going into the first transformer, where we've got a couple, you can't probably tell there, but there's a couple diodes here that lead into this potted area. There is an IC hiding down there that does something. I don't know what. I don't even know if we'll know what IC it is. And we've got a couple more diodes. Another IC that actually looks like it is... I don't know what that is. That could be a rectifier again. It's real hard to tell right now with the way that everything's going. And the other side of the transformer, big fat diode, more potting, some caps to provide some line filtering, what appears to be a transistor, and some varistors. So let's see what there is to learn, and let me also turn off that. I don't know. What do you think we can get into on this, if anything? We've got the RJ45. These are not MagJack. Well, maybe they are. You know something? Instead of guessing, I think I just need to start taking things apart. I think that will make the viewers at home rather quite happy. So let's see if we can't get into this. And while I'm waiting for the soldering iron to heat up, let me tell you about a couple features that I see here. One, I don't know if you can see this gunk all over this board, but this board is in dire need of cleaning. You never want to leave a board, especially one with high voltages, dirty, because it really decreases the overall creepage that you have in place. It provides paths for carbonization and for short circuits to form. The reason that you have these big spaces is to prevent that. You don't want a high electric field gradient between any two spots. So any place on a board where you see that they've cut away the copper, that is to satisfy creepage and clearance regulatory compliances so that we don't create a short circuit. But man, it would have been nice if they would have cleaned this. So everything over here appears to mostly be the part of the board where all the high voltages are switched and flipped and they do whatever they do with them. Now there is an IC down here. I don't know exactly what that does. It could be that they're jumping up to higher frequencies. I don't really know. We could pull out a scope and find out, but I hate doing that on a line powered device without an isolation transformer. And I don't have one handy. And it does look like they utilized two-sided PCB assembly with a combination of through-hole and surface mount devices, and that is not cheap. Something else that's kind of interesting is they left these pins to float. Right? These are part of the RJ45 jacks. See right there? There's 1, 2, 3, 4 pins that they never even bothered having soldered into place. There's not even pads for them. That, I don't know, it's surprising. I'm surprised they didn't just leave pads. But maybe they had their reasons. So you've got the 4 what must be signal pins, and then they're injecting power onto these other 4 pins right next to them. Interesting, interesting. All right, we should be heated up sufficiently at this point. So let's see if it's not possible to do a tiny bit of disassembly. Let's see if we can't get into those mag jacks a little bit. By the way, for those of you out there in TV land right now, you're welcome to ask questions. I will be happy to try to answer them as I go through. Maybe you want to know more about the board. Maybe you want to know more about me or the tools I'm using. Maybe you'd like to know the name of my cats. That's an easy one. We've got Moxie, Chester, and Fat Ollie. I know what you're wondering. Is Fat Ollie named so because of his weight or because he's a really cool cat? A little bit of both. So right now I'm using some desoldering braid, just heating up each one of these pins, and I'm trying to soak up the solder from the through-hole connectors. And if I can get enough solder out, we should be able to remove this without much work. I did order some solder removal alloy, but it's not in yet. Last time I was trying to desolder something, I was using some rosin that I think was just well past its prime. And it did not go well on our previous teardown. Something else of note, we missed Mark Voids of Warranty last week. I had a neighbor knock on my door and tell me that the electric pole, the telephone pole outside our house was leaking. And I said, I think I misheard you. I thought I heard you say that our telephone pole was leaking. She said, yeah, it's leaking water, a lot of it. Now, I said, I think there's a mistake of some sort. Telephone poles don't leak water. They don't have any way to get water in them to leak out of it. Let me walk out with you and we'll see what there is to see. So I went out with her, and wouldn't you know, our telephone pole was leaking. A neighbor had a 1-inch water main that apparently had a leak somewhere along it, and it found its way into one of the conduits that goes from the telephone pole to the neighbor's property. So how about that? The water would go through the conduit under the ground, and then it was under enough head pressure that it was able to come up and out the pole. So there are some ground shield pins that I am trying to desolder now. The issue is that they require a lot of heat. And I might need to adjust the temperature of my iron to be able to do it. Let's see. So what I'm trying to do right now is remove these two RJ45 connectors. They might in fact be mag jacks. We're going to find out here. Oh, looks like I missed a pin. I'll grab that before I forget. The pins don't require nearly as much heat, so they come off pretty readily. But the ground shields require a ton of heat. They are much more difficult to get out. This is where I wish I had my buddy Sebastian watching. He could advise me as we go on how to get this done a little bit quicker. But does Sebastian watch? No, he doesn't. Some friends, I tell you. All right. So I just... oh, boy. I just applied a little flux to each one of these. And it is making some smoke. Come on. Okay. We're just making incremental progress, removing as much of that solder as possible. In a second, I'm going to get a screwdriver in between the mag jack and the thing, heat everything up again, and see if I can't yank it right off. Should be fun. My favorite little kit of often used screwdrivers. There's one. I think there's still a little too much solder left there. So let's see about that. And remember, out there in TV land, you can ask questions as we go. I've got a screen up. All right. Now, I was curious as to whether or not these are in fact mag jacks. And when I say mag jack, what I mean is magnetic. And that would indicate that there are in fact little tiny transformers embedded into these things. You always need some magnetics. It's just a matter of whether or not they end up on the board or they end up in the case. And it looks like we've got a situation where there are there's really no room for magnet. Well, maybe there's a little bit of room back there, but it sure doesn't look like it. Let's see. Okay, so here's our RJ45. This is the part that would connect. You know, we're essentially looking at the same thing, you know, right here. Okay. And this is basically how they work. You've got a little piece of spring steel that when you plug in your let's see if I have a network cable handy. I might not. But when you plug in your little network cable, the connector, how do I not have one handy? Oh well. But the little plastic connectors makes contact with each one of those little tiny little baby pins. And we've got no magnetics handy. There's just wires going into a case and then going into the pins that come out the bottom. So this device then looks just like one of these to the cable. It looks just like a pass-through connector. There's no conversions going on. So anyhow, I don't know if there's anything else we can learn from this at this time, but if time permits, I'll come back to this in a couple minutes and we'll see if we can't learn anything from any of these other components. I don't know that we will, but you never know. All right, so here is our Ubiquiti Unifi device, and we're going back to a overhead view, find the right connector. Okay, it is free and clear. I see where the magnetics are, right there. We'll look at that in a second. So what do we need to do to get this out? Are there any screws hiding under that sticker? I don't feel any. It feels like it's stuck on something. Well, it just came loose. Okay, I'll take it. All right, so we just have a injection molded case. An injection molded lid. Looks like it's starting to yellow a little bit. And there's a semi-opaque clear plastic piece there that must transmit some RGB LED or some LED color up around this ring to give it a cool effect. It does look cool. Wonder if we can see that. Oh, yeah, it's that tiny thing right there. Let me bring it back into a close-up view. So it looks like that wee little tiny diode right there is what was illuminating that whole thing. All right, so here is the inside of the Ubiquiti Unifi. We'll just take a quick look around and then I'll describe what a few things are. And there are a couple neat things to learn, I can already tell you. And then the back side / bottom side we've got right here. Another RJ45. All right, so let's start looking at it. So you plug the PoE, the power over Ethernet, so you've got your signal and your power that comes in here. We've also got a little reset button there, so that's nice. And the signal goes from here over to the magnetics. This is what I was looking for, hiding in the case of that other one. Here you've got these little itty-bitty tiny coils of wire that isolate the signal from here from the rest of the circuit. That's important because every now and again you get noise and, you know, maybe you get, I don't know, high voltage ESD discharge or whatever. And it can go in and it can damage your circuit. So you use the magnetics to isolate that. You use the magnetics only detect changes in signals. They don't really care about any steady state condition. They just care about changes in that condition. Now, the unusual thing is that the magnetics are so far away from the connector. Typically, you'd want to bring those much, much, much closer. So we still see schmutz on the board. So again, they didn't feel the need to clean their boards. Never a good practice. Talk to Mike Conrad over at Aqueous Tech, and he will give you 1,000 reasons why you should clean even no clean flux. Anyways, after the signals make it through the, you know, resistors and capacitors and, you know, ESD diodes and whatnot, they hit the magnetics and then they leave, and you've got a TX and RX differential pair that goes over and makes it into, look at the number of pins on this thing. That is a lot of pins. Looks like it says Atheros. Can't really see. You guys might be able to tell at home. I'll have to wait until I get the microscope view out. But man, that's a lot of pins. And from here, we've got a ton of traces that run over to what must be memory. I don't recognize any of those top side markings. 1412G, is that a MAC address? Possibly. I'm guessing that's a memory, maybe a RAM, and maybe over here with fewer pins, perhaps we have a ROM. It would help if I pull out the microscope. That's probably my next move. From here, we've got the wireless part that is isolated with via fencing, which is pretty neat little trick there. That's something to look at in a minute. And we've got two antennas, one left, one right. Little diversity antenna system going. Signal in, signal out, ground 3.3. So we've got a little UART interface and what must be a programming header. So we've got 1, 2, 3, 4, 5, 6, 7 pins in use there. All right, let's get over to our microscope view and see if there's more that we can learn. I think there is. Let's see if we have microscope up on one of our macros. Looks like we do. All right. So here is the big chip. This guy has a ton of pins coming in and out of it. I don't even know how many, but it's a lot. All right, so we've got the Atheros AR7241AH1A, and I'm not familiar with it, but my guess is FPGA, based on the speed this device needs, as well as, there's a little bit of schmutz there, that's weird. Based on the speed, as well as the number of pins that this thing's showing. Usually anything bigger than this, and you'll start hitting bottom termination, you know, BGAs and whatnot, but maybe it was a little bit cheaper for them to do it this way. So coming out of this, we've just got a ton of signals. Here we've got a couple capacitors, and it looks like these might just be decoupling capacitors. You can see some interesting things that they're doing with the traces that are making them unnecessarily long. That's length matching, so all the signals arrive in the same spot at the same time. Here's something interesting that we haven't seen on Mark Void's a Warranty yet, and that is a little resistor array. So instead of having 4 separate resistors, we just have 4 all tied together at 220 ohms. So the signals either go into or come out and then hit the resistors, and then they hit this device. Now, I don't know what we have covered up there. Those have to be internal tags. You don't see those on ICs. Everything is lasered anymore. But I don't know if I can get those off cleanly enough. Nope. I can't even get my fingernail under them. Not much I can do for that one. Okay. So anyhow, on the other side of this main IC, let's see if we can get a little better focus going. We've got, what does this say? MXIC B134883. So this is an MX25L6408 EMI. Here's something else we haven't seen on Mark Void's a Warranty yet. Whatever this company is. I don't know. One of the few I have never run across before. But my best guess is this is RAM. So one of the things one of the things I noticed on this, anytime they have a copper pore that's just kind of floating out in there, they have it tied down to another layer. That's to prevent this from turning into a little antenna. Something very important on an RF board. And to make sure that this thing gets lined up just right, they've included some placement fiducials. And that's probably just with such a fine pitch, they wanted to make sure that this thing didn't end up bridging between 2 pins or whatever, you know, when it put it down. And then everywhere you have the copper pore, you can see that they just dotted it with vias all over the place until we get to here. And here they put them at a very specific spacing. Whatever frequency that they are operating at here, I'm guessing 2.4 gigahertz. You want to make sure that these things aren't spaced in such a manner that any signal can get out. So you take the data lines, the RF lines, and depending if you're doing microstrip or strip line, so if you're running them along the surface or if you're running them down into the body of the PCB stack, you want to make sure that by the time you get over here, that the wavelength is greater than the spacing between here. And I forget right off if that's by a factor of 2 or a factor of 4, but you want to make sure that any signals that are trapped in the board can't make it through to the other side of this. And that's what these vias are doing. This is called a via fence, and it encapsulates the RF side as much as possible. All right, so this is our RF connector here. We've got, oh, that's interesting. So it looks like if you want to use the external connector here, you just rotate that R26 up here into the R27 position, and then you can tap and test that antenna. So we've got part of a Pi network. They designed in some pads for capacitors that they ended up not using. L75, so an inductor. And then over here, and then we've got those big sheet metal antennas that I pointed out earlier. That's interesting. Let's see what else we can find. Same thing on the other side. So it goes through, let's get back to give me a second here to find where I put my screwdriver. There we go. So it looks like we pass through a large array of capacitors and resistors that they're using to balance the transmission line before it becomes a transmission line. Interesting on this side that they started to populate some of these capacitors. So they found the need to balance it on this side that they didn't on the other. Same resistor, manual resistor switch. Oh, nope, so that, I must have missed that on the other side. So they're just balancing this transmission line as they go along. It is kind of long. Until we come over and we're into the antenna. So just a couple things to point out. So they gave plenty of spacing, plenty of airspace between the copper ground and the antenna. You want to keep that, relatively consistent as long as you go around. But if you keep it far enough away, the general idea is that you don't leak too much energy from the antenna in over here, and you get a relatively consistent impedance. And then they did the same via fence deal that we saw over in the other part. And again, it's just to try to keep the signal here from infiltrating the ground layer and becoming a problem in other parts of the board. What else do we have to see over here? I don't know. Let's get down into the connector and see if there's anything of note. A couple plated through holes. What they're doing, I don't know. Look at all that schmutz. That is all flux that should have been cleaned off and wasn't. So, go figure there. Oh, you know what? I bet those holes are for LEDs. 1, 2, 3, 4, 5, 6. Yeah, so there's 8 pins for 8 conductors. I bet you those other two, at some point they had a different connector in here that had a couple LEDs that they weren't utilizing, but they still had to provide holes for the pins. Couple 0 ohm resistors. So you can use these for two things. One is as a jumper. It doesn't appear that they're using them as jumpers here because they could have very easily just run a trace from here to here. it could still be that they used them as electrical jumpers, testing, something along those lines. I'm not sure. But the other thing you can sometimes get away with is using them as RF chokes. I mean, you're cheating a little bit, but you have something. I don't see them using them that either. Well, I guess. So you come up, basically you make any RF noise go up and travel at right directions, and that kind of mutes it a little bit. BHRZ. I don't recognize those top side markings either, but I am going to guess that's some sort of a electrical component. That's my guess, that it's an electrical component. Prove me wrong. I don't know what that is. I'm just looking for other interesting things right now. So we've got an inductor right on the board surface. So they're doing their electrical rectification and control right there. There's us a little light emitting diode and its current limiting resistor. This is our programming header. Some sort of a debug interface. It was really, I mean, you don't really see people do that. So good on Ubiquiti for, populating that thing. That's really cool. So my suspicion is they programmed and debugged this every device that comes out of their shop. Otherwise, they wouldn't have bothered populating those until they RMA'd them. So that's really cool. Another, what I imagine to be some sort of a voltage regulating IC. I'm not entirely sure. And then we're back into the RF section. So the things to note that they did a good job on, I mean, there are vias everywhere. Multiple vias tying different things together. That provides nice low impedance paths for the charges to go. You've got vias stitching all of the copper pores all over the dang place. And that's great because if not, these things become antennas. And let me back out for a moment and show you what that looks like. Give me just a sec here. All right. So here is our board once again. This piece of metal, just this weird looking F shape, is an antenna. Amazingly enough, that is an antenna. And it's just a piece of metal, but it happens to resonate at a desired frequency. Now, the issue that you run into is it doesn't just have to be something that you intend to be an antenna is an antenna. Any piece of metal that's the right dimensions can be an antenna. And something that's, roughly that big, well, you can actually see this little copper pore here. If you're not careful, that can become an antenna and radiate noise all over your board and make it so that you don't pass EMC testing. So you always have to tie those with the ground so that they're not able to resonate. And that's what they did. I mean, if we look on the back side, look at all those vias. Now, the only trick there is when you're designing is to make sure that you have a safe aspect ratio is 10:1 these days, without having to have, fancy pulse plating and high expenses. So this is this board's about, if I had to guess, this is a 63 mil board. I don't have to guess. I've got calipers right here. Let's find out. All right. So if I'm being honest with you, it's 61. I was off. Oh, wait. Yeah, if I'm not being honest, if I nudge it a little, I can make it 63 pretty easily. Look right there. Oh, wait. No. Let me go back. Oh, no. Look. Oh, no. There. Darn it. Okay. It's not exactly 63. It's a little thinner. Ever so, there we go, 61. If I measure it right here at this location on the board, it's 61, which is really close to 63. You got to give me that, right? You got to give me that. But basically what that means is those little holes, the smallest you'd want to make them is 6.3 mils. Well, we don't have drills that are exactly that size. You know, we would round up to the nearest 0.5 millimeters. But you could pretty easily get a 6 point, you know, or 6.5, 7 mil hole and have it plate. We would drill it a little smaller, plate up to that size. Or if you can go even bigger, do that. Make it a 10 mil hole. I mean, there's plenty of space on this board for those bigger vias. Might as well do it. You'll get more consistent plating. It's easier to get the fluids in there, and you'll overall get a higher yield with fewer problems. So do that if you can. So with that, I don't know if there's really that much else to look at on this board. So let's take a minute to back out and go back to that power board. That looked like it was a bit more interesting. All right, power designers and RF designers are typically two different kinds of people because they have to worry about different things. Power designers have to worry about creepage and clearance, magnetics, locating your transformers where you do, and having them at right angles and all that good stuff. And RF designers just, I mean, it's a different breed of stuff. So what I'd like to do, if I can, is get a hold of one of these transformers. And I was just trying to eyeball which one. They both have glue attached to them. This one has the least amount. So I'm going to go ahead and extract that. And what I want to do is see if I can't show you how these things are made. Again, feel free to ask questions. It's a rather quiet day on Mark Voids a Warranty. So I'm going to heat up the joints. There's a lot of metal on this, so you've really got to dump a lot of heat into this to get it to warm up to the temp that you want. I'd be better off with a different tip, but I don't want to wait till my iron cools down to change it out. But you put the flux on, you put the solder braid on, you heat it up, and once the solder melts, it should wick into the solder braid. And if that doesn't work while it's hot, you can just take it and give it a little whack and get some solder out. But the issue is that this stuff doesn't seem to want to melt. A little thicker solder braid wouldn't hurt either, but we're doing this live. We can't be bothered with stopping to get the right tools. The other issue that you have is RoHS stuff, reduction of hazardous materials. So the lead-free solders melt at a higher temperature. So it wouldn't hurt if I turned up the temp a little, but Again, we can't stop for trivialities. We're doing this live. On a side note, while we're doing this, I just got new flux. It does make a difference. Flux goes bad over a while. So make sure you're using yours and reordering when necessary. Okay, we're making progress. How many more pins need to go to get to what we want? Looks like a few. So thanks for bearing with me. You guys want to hear a quick electrical or electronics joke while we wait? What do you call a store that only sells resistors? The Ohm Depot. Kill me. Don't worry, folks. I'll be here all week. Don't forget to tip the wait staff. Oh, I think this is a different component, but that's okay. The amount of time that I'm leaving this iron on the board is problematic. If I was trying to save the board, I'm not. But electrical components and heat don't go well together. Some things are sensitive, some things aren't. Your board itself has something called a glass transition temperature, where the fiberglass epoxy blend, the fiberglass part of it actually starts to liquefy and become pliable. It can move, and it can actually start to decompose if left long enough. Your components, like that varistor on the other side, some of those, depending on how they're made, they can actually be, react rather poorly to the heat as well. Tantalum capacitors, for example, they end up crystallizing, which isn't good. All right, let's get a screwdriver under that and see if it's ready to move. Well, I just spent a while desoldering several things. Did I desolder things? Yes, I did. Were they a transformer? No, they weren't. Oh, man. Whoops. I got a little too excited there. See, you put the cameras on me, and I lose all sense of the world around me. That's okay. We'll get there. There it is. Okay. So this is the transformer that I wanted to get to. What we see so far is that we've got 4 pins there's going to be, the plastic core. Inside here, there's going to be some amount of a ferrous compound. And it looks like whoops. Looks like I broke it a little bit. Oh well. It looks like this has two positions that you can put this ferrite core. One is the one it's at, and the other one is folding it over to the side. Ferrite is rather brittle, so it doesn't take much to break that off. So we've got tape and 2 coils of copper. So what happens is you put current through one of these and it goes around and around and around and around, and that creates a magnetic field that points in this direction. So it transfers through that ferrite core. I don't think I can push that out, but it travels through that ferrite core until it reaches the other side, and there is another coil of wire. Well, that just senses the changing magnetic field. That changing magnetic field induces a current that goes around and around and around over here too. In that way, you can isolate this side from this side. So it will only respond to the changes in current. It doesn't care about steady state anything. It just cares about changes. So if there is, a 10 volt DC bias, that can get eliminated between this side and this side. And by running it back over, you guys saw me do this. I broke these off. But by running around in 360 degrees, they can greatly increase the confinement of that magnetic field inside this little loop. So you don't have to worry about magnetic field lines shooting off in all directions, out in front of this and creating, inducing currents elsewhere. Most of it'll get just picked up and wrapped back around in that other direction. So that's what's inside pretty much every transformer. All that really changes is the number of windings. You can trade off current and voltage depending on how many windings you have going in and how many windings you have coming out. This looks like it's pretty much a 1-to-1 winding. So it's just meant for isolation. But you could do 2-to-1 or 4-to-1 or 8-to-1 and either get high current or high voltage depending on what you wanted. So we have about 7 minutes left. I wonder what else there is to see, if anything. I don't know. We've got capacitors. If you've never had a chance to open these up, it's interesting, but I'll warn you, it's a little stinky. But basically what you've got are 2 pieces of metal foil that are laid one on top of the other and then rolled up into a coil. Resistors aren't that fun to take apart. It's just a wire, and then just a bunch of stuff. Sometimes there's wire wrapped around. This, my suspicion, is just a fuse. Yeah, that's about it. And that's probably about it over here too. Well, we have yet another board to put on the graveyard of Mark Voids of Warranty. If you haven't heard me say it before, I've said this in a lot of our very, very beginning ones. You should take these and nail them up on your wall and leave them there as an example to all the other boards of what will happen to them if they're not good to you, right? Electronics, they like acting all tough and rough, and they like to try to keep you from, getting your job done. No. Threaten them. Let them know. All right, folks. With that, I think it's time to end Mark Voids of Warranty. It's been fun. Next week, we're going to take apart something else, and it might just be this video card here. I don't know. But if you can help me, I would appreciate it. I need more subscribers. Once we get to 500, I get to take apart this giant lens sitting behind me right there. That thing is huge. It's off of a production TV camera. It's big. I want to see what's inside, but I can't yet. Every day we get a couple more. We're close, but I need your help. Tell your friends, tell your neighbors, tell your friends' neighbors, tell your neighbors' friends. Tell them to subscribe and like Mark Voids of Warranty. And sooner rather than later, we'll all get to take apart that. With that, it's been fun. If you ever have any assembly needs, visit aapcb.com. Thanks so much, and bye.